Swayam Prabha. Digital India. Educated India.
Hello everyone, once again welcome you all to MSP lecture series on advanced transmetal chemistry. This is 12th lecture in the series. In my previous lecture I had initiated discussion on valence bond theory and I did discuss about various hybridization concepts and also with respect to transmetal compounds. I discussed selected electronic configuration such as D5, D8 and I showed how one can form different type of complexes and one can explain the bonding using valence bond theory. So, now let me continue from where I had stopped. You can see the table I have given here. I have covered almost all hybridization you come across for transition metal complexes. For transition metal complexes having different ligands and also having different geometries and hence different hybridization they have used. Look into the first one. Here arrangement of donor atoms or ligands is linear with respect to central metal atom, and when the coordination number 2 is there, invariably we use sp hybridization. Example, diamine silver complex. Next, trigonal planar with coordination number 3. Here example I have given is Hgi3 minus with sp2 hybridization, and of course tetrahedral you all know that we use sp3 hybrid orbitals. We have several examples, just I have given one example here, tetrabromoferrate. Then square planar, most of the D8 metal complexes invariably show square planar geometry along with D7 S2 system with +1 oxygen state. Okay, for example, rhodium and iridium along with nickel, palladium and platinum, that is square planar. The hybrid orbits we are using is DSP2, and the trigonal bipyramidal, the hybridization is sp3d. I have given one example of copper here, and you should remember, for example, when we move to square based pyramid, again we are using sp3d. That means we should be able to differentiate between the d orbitals that are involved in these two hybridizations. If you look into trigonal bipyramidal, we have two ligands in the axial position. So, we need to use dz square orbital, and hence here the hybridization of sp3d involves dz square, whereas in case of square based pyramidal 4 ligands are in the plane. So, we need to use orbitals that are oriented in the plane or along the plane. So, that is the reason we use here dx square minus y square. So, hybridization is same, but the d orbitals are different in these two cases, that one should remember. And of course, in case of octahedral we are using sp3d2 for outer orbital complexes or d2sp3 for inner orbital complexes. Just I have given one example, hexamine cobalt. We have numerous examples for both the cases, inner orbital as well as outer orbital complexes. When we go to coordination number 6, we come across another important geometry, that is trigonal prismatic, and here also the hybridization is essentially the same, sp3d2, but the orbitals we are taking among d are different. One such example is we can take S, Px, Py, Pz, and then xz and yz are taken here, not dz square and dx square and y square we prefer in case of octahedral complexes. But when the early metals exist in their highest possible oxidation state, we can as well consider inner d orbital instead of taking p orbital, and hence many triangular prismatic complexes utilize all d orbitals along with s to have a hybridization of sd5 instead of sp3d2, and this is true with metals in their high valence state, especially metals having d1, d2, d3 electronic configurations. And then when we have coordination number 7, we have pentagonal bipyramidal geometry. So, in this case, since we need 7 orbitals, we are using additional one more orbital from d. Here it is dx y, dx square minus y square and dz square along with s and 3p orbitals. Example I have shown here, sp3d3 pentagonal bipyramidal. But when you have 7 coordination, we can also have another geometry that is called capped or monocapped octahedral geometry. So, in this case also sp3d3 is there, but the orbitals are different here, you can see here. In the same way, when coordination number 8 is there, we come across 3 different types of geometries. One is cubic, one is dodecahedral, one is square antiprismatic. In case of cubic, we use sp3d3f, that comes to our f block complexes, and then in case of dodecahedral, coordination number is 8, we are using sp3d4 here, we are using sp3d4, and then I have listed all dz square and all dxy, dyz and dzx are used. And then dodecahedral geometry, when we have square antiprismatic geometry, again sp3d4, and here except for dz square all d orbitals are employed in this hybridization scheme. And example is this octafluoro tantalate 3 minus, and then the last one with coordination number 9, the most symmetric geometry you can think of for coordination number 9 is trigapped trigonal prismatic. And here this is an example where all valence orbitals have been utilized in arriving at a hybrid scheme having the composition sp3d5. This is sp3d5 hybridization. Example is ReH9 2 minus. Here 9 metal to hydrogen bonds are there, and this is one of the rare examples of homoleptic hydrates having as many as 9 metal to hydrogen bonds, and this has a tricapped trigonal prismatic. So, now to make you familiar with some of these geometries, I should show you, it becomes very clear, and then also you should be able to distinguish between trigonal prismatic and octahedral geometries and what are the difference between them. So, if you can see here, this is trigonal prismatic geometry. You can see this one, this is a trigonal prismatic geometry. And now I have here octahedral geometry here, and then is there any alternate name for octahedral geometry? Yes, this is trigonal prismatic and this is trigonal antiprism. If it is trigonal prism, this is trigonal antiprism. So, then how they are related? It is very simple. You take this one, and if you see these two triangular faces, they look eclipsed, right? They look eclipsed here, and whereas if you look into this one, if you just try to see this triangular face and this triangular face, they look like staggered. That means this is a trigonal antiprism, staggered one, and where we have eclipsed one, this is trigonal prism. But is it possible to convert? Yes. Just see, keep this one and turn this face something like this, and then you have to connect this one with 3 more sticks, then you can get octahedral geometry. So, this is the relationship between trigonal prism and trigonal antiprism or octahedral. So, now this is octahedral, and then you go back and see them eclipsed, this is trigonal prism. You take this trigonal prism and make one of the face staggered, and you can visualize octahedral geometry. There should not be any confusion between these two geometries. I have shown those things here. So, this is trigonal prism, you can see the relationship of these two triangles, they are on same side. That means, if you just bring it towards the screen, then what happens? They will be eclipsed, whereas here you can see you take any two and they are staggered. Similarly, we can compare this tri-capped triangular anti-prismatic geometry I mentioned in case of ReH9 2 minus for coordination number 9. You consider this one, you can see here we have 1, 2, 3, 4, 5, 6 vertices are there, and then on each of rectangular faces if you put one more vertex and then connect it with 4 bonds, then this will be monocapped, and then if you put one more here and connect it with 4 bonds, this will be bicapped trigonal prism, and then one you put here and make bonds with here, then this become tri-capped trigonal anti-prism. Okay. This is what the geometry adopted by ReH9 2 minus to accommodate 9 hydrogen atoms surrounding rhenium atom. You can see this one, this is monocapped and this is bicapped and this is tri-capped trigonal prism, and you can distinguish these 3 new vertices added. So, total vertices are 9. So, this is tri-capped trigonal prism, and similarly you can take for coordination number 7 octahedral is there, and besides pentagonal bipyramidal another possibility is monocapped octahedral geometry. So, you consider one of these faces and add one more vertex and connect it with the 3 more bonds, then that becomes monocapped, something like this. Yeah, you can now distinguish the 7th vertex coming here. This is monocapped octahedral, and this is cube now. The same thing with cube is there, and in the cube you take this square then turn it, okay, so that both of them are not eclipsed. So, you take this yellow face and rotate it so that this will be staggered, that means vertex will be pointing here, okay, turn it. So, something like this. So, now connect them in this each square you put one more, so that you will end up with 2 equilateral triangles, and on 4 sides you will end up with 2 equilateral triangles, so that you will be having 8 equilateral triangles, and then you have 2 square faces. This is called square antiprism. Sometime coordination number 9 one can also have monocapped square antiprism, sometime you can also have another one below, so that you can have bicapped square antiprism. So, this is for coordination number 10. Okay, this is the most common one. In some cases coordination number 9, instead of adopting this one, they can also adopt this geometry having monocapping on square antiprism. It is bicapped here on these square faces, then it becomes bicapped square antiprism. Even I have that example here, you can see this is how it looks like. So, this is one face, okay, and this is another face, and they are staggered to each other. When they are staggered to each other, you can clearly see these 8 faces here, 8 equilateral triangles. So, you can count them, there are 8. So, this is all about, I wanted to tell you about the geometrical difference between various polyhedra. So, in the beginning I made a statement, number of hybrid orbitals formed equals number of atomic orbitals mixed. Is it really true, or is there any exception? I shall tell you in a couple of minutes answer for this one. And then type of hybrid orbitals formed depends on the types of atomic orbitals mixed, that is absolutely correct, no issues, and many types of hybridizations are known. You saw all possible hybridizations I mentioned, and one more thing you should remember, when we have octahedral geometry with metals in their high valent state, especially with early metals, it is not just sp3 hybridization. You should remember one more thing, when we talk about tetrahedral complexes of early transition metals or metals in their highest possible oxidation states, not necessarily they utilize sp3 hybrid orbitals, sometimes they also utilize all the d orbitals, okay, thus showing d3s hybridization. That is quite common with high valent metal ions, example titanium tetrachloride. If you take, titanium is not sp3 hybridized, environment it is utilizing, but it is utilizing d3s, and similarly if you take potassium dichromate, chromium is using d3s because this inner d orbital, and it is essentially using 3d and 4s. So, it should be d3s, and similarly in KMnO4 manganese utilizes d3s, and osmium tetroxide, osmium is in plus 8 oxygen state, this also utilizes D3S while forming osmium tetroxide. However, the most common types of hybridization observed among main group elements are sp, sp2, sp3, sp3d, sp3d2 or in some cases d2, sp3. I put a question mark here, you can see number of hybrid orbitals formed equals number of atomic counts mixed. It is not true, there is an exception here, that is what I want to show you here. Look into this one. Here we come across 2 SPD hybrid orbitals, that means 3 orbitals are involved, one PZ, one S and one DZ square is involved, and but still we are ending up with only 2 hybrid orbitals SPD oriented opposite to each other in this direction. So, these empty orbitals can take readily from ligands to establish a linear molecule. The example is diamine silver plus complex. So, how that happened? The hybridization of S, PZ and DZ square with the choice of phases shown here produces a pair of collinear orbitals that can be used to form strong bonds. In order to form strong sigma bonds, some metal ions utilize this kind of hybridization, very rare ones. You can see now, so these 2 SPD hybrid orbitals are oriented in this direction. Now, if 2 ammonia ligands are coming, they donate a pair of electrons to these empty orbitals to form strong diamine silver complex. Okay, this is the complex here, and in order to interact, the energies of Nd, okay, that is 4d and n plus 1s, 5s and 5p should be similar, true with heavier elements. So, energy should be very comparable, and if you go for heavier elements, the energy difference marginally remarkably decreases as a result, and also the size increases, they diffuse into each other. Because of this one, what happens, in order to strengthen metal to ligand bond, they utilize this kind of hybridization. In fact, molecular orbital theory also suggested a significant mixing of s, p and d orbitals in this complex. Now, I will show you another interesting hybridization, looks very similar to ethylene, but how they utilize in a different way to facilitate metal to metal multiple bonding, especially in case of main group elements. So, tin 2 organometallics of the type 2SN with bulky organic ligands containing tin 2 carbon sigma bond, containing tin 2 carbon sigma bonds are stabilized only if R is sterically demanding. That means, in order to stabilize metals or elements in their low valent state, okay, you have to have bulky groups, they will give umbrella protection. One such example I have shown here, when you react SnCl2 with very bulky ligand such as this one, it forms di-coordinated tin compound, and then this is monomeric in solution, but dimeric in solid state, but the dimer does not possess a planar SN2R4 framework, very similar to ethylene. Ethylene molecule is planar, you can see simply something like this, okay, it is something like this. In contrast, okay, this tin dimer has a different structure, and another interesting thing is SN-SN bond distance is 267 picometer. This is shorter than a normal single bond having a distance of 276 picometer. That means it is slightly smaller, but that is good enough to evoke a multiple bond character. That means this has some multiple bond character between 2 tin atoms, and then thus SN2R4, this dimer has a trans bend structure with a weak tin-tin double bond. Now, using hybridization concept, is it possible to explain this trans bend structure? If it is a planar structure like ethylene, no issue, simply you can say it is sp2 hybridization, and there is 3 sp3 are there on carbon, 2 sp2 hybrid orbitals are utilized, 3 sp2 hybrid orbitals are there on carbon, and 2 sp2 are utilized in making 2 CH bonds and 1 for CC bond from each CH2 fragment. Okay, now what it happens, but the structure is something like this, okay, and in case of ethylene we have something like this. So, no issues with this one, sp2 can very easily explain the bonding here. But if you see here, what would happen, similar to carbon, it also undergoes sp2 hybridization here, but in this case what happens, one of the p orbital is left unutilized, but not left with an electron but empty, and now we have 3 sp2 hybrid orbitals are there and 2 sp2 have 1 electron each, whereas the third sp2 has 2 electrons. So, that we have 1 p orbital without having any electron. So, now they orient in this fashion in order to see this kind of Lewis acid base type of bond formation. Now, this acts as a Lewis acid and now this acts as a Lewis base. Similarly, this empty p orbital on this tin acts as a Lewis acid, whereas this filled sp2 acts as a Lewis base. So, in order to facilitate this kind of overlapping, this orientation has to be in this fashion. See, it is not like this, it should be something like this. When they rotate like this, what happens? Empty p orbital on this tin atom will be aligned towards this one, so that they can have overlapping. So, now we have 2 electrons here and 2 electrons here. It is not really a strong pi bond, it is not a sigma bond either, but it is intermediate between that one. We have still 4 electrons between 2 tin bottoms, 2 tin atoms, but because of this kind of overlapping, what happens, they do not really represent 2 strong bonds, whereas they are relatively weak. Nevertheless, they add some multiple bond character and hence the SN bond distance decreases to 267 from 276. And now you can see very interesting sp2 hybridization, and in fact if you look into multiply bonded compounds of main group elements, whether you take arsenic, bismuth, even lead or silicon, in all these cases this is what exactly happens. This kind of sp2 hybridization takes place, and in order to facilitate this kind of overlapping, they have to take this kind of alignment. As a result, they have a bent structure. So, that means successfully you can explain this trans bent structure using this hybridization concept. And what are the limitations of valence bond theory? When we talk about limitations, that limitations are more or less confined to its utility among coordination compounds. That means it does not explain the color of the compounds, that is spectral properties. It does not explain fully the magnetic properties, especially the temperature dependent magnetic properties, and also it gives emphasis for spin only values. When you go for 4D and 5D, most of the metal ions do not obey experimentally determined values. Experimentally determined values are always different from theoretical values calculated from spin only, and valence bond theory does not explain these things and does not explain relative stability of complexes. Once you have coordination number 4, it can depict whether tetrahedral or square planar, but relative stability of complexes, okay, with different ligands, answer does not come from valence bond theory. That means it does not explain about strong ligands and weak field ligands, does not distinguish between different types of ligands, it does not distinguish. As far as valence bond theory is concerned, whether you take cyanide, whether you take carbon monoxide, whether you take triphenyl phosphine, ammonia, it is just a ligand having a pair of electrons that is coming towards the metal, that is it. In general, VBT gives emphasis for localized bonding model. Again, what happens, it will try to confine a pair of electrons between the 2 atoms through overlapping. Okay. That means, if there is some delocalization, there is no answer from valence bond theory. So, these limitations are sufficient to look for a better bonding concept to explain various aspects related to metal complexes. That is where crystal field theory made its entry into coordination compounds. So, in my next lecture I shall tell you more about crystal field theory with an interesting background to this crystal field theory as well. With this, have an excellent time reading chemistry.